In this lesson, we're going to look at how to apply the definition of a derivative in order to find derivatives of some functions. We'll begin by reviewing the definition of a derivative, and then we'll look at some examples in which we make use of that definition. So let's recall the definition of a derivative. Derivatives are related to two other things we've been looking at, slopes and rates of change. Recall that if we have a function where y is equal to f of x, the derivative of that function f is another function that gives us the slope of the tangent line of f at different values of x, whichever value of x we choose. And we introduced a couple of different symbols to denote the derivative of this function. We can write f prime of x, a version of Newton's symbol for a derivative, or we can write something like dy dx, a version of Leibniz's symbol for the derivative. Either of those denote this derivative function. And in Newton's notation, this prime notation, we can say that f prime of a, the derivative of f at a for a given input value a, is either the slope of the tangent line of the function at a, if we want to think of it graphically, or the instantaneous rate of change of the function at a. And then we also sometimes say that we are finding the derivative of f at a, which will be a number rather than a function. But these are all synonyms of the same thing. And we introduced a definition of this derivative function as a limit of a difference quotient. So f prime of x can be defined as this limit right here, the limit as h approaches 0 of f of x plus h minus f of x over h. And if we want to work on that limit, either to evaluate it for a given value of x or to simplify it as much as possible in order to produce some kind of purely algebraic expression for it, we can typically do that by using the method of simplification for working with limits. What we'll usually end up with then is another function of x, which we can call f prime of x. And then if we want f prime of a for some numerical value a rather than a variable like x, then we just use the same limit, but instead of x appearing in there, we will have that constant a in its place. Another way to do the same thing is to start by finding f prime of x for any value of x, and then find f prime of a by evaluating that f prime function where x equals a. So that's a review of what we've done up to this point. Now in this lesson, we're going to use that definition of a derivative to find derivatives of some familiar functions. Now this is going to require some fairly heavy-duty algebra in at least some cases. We're going to use binomial expansions. We're going to have to work with complex fractions. And at one point, we'll use something called the conjugate of a radical expression. Before long, we will have some formulas that will make the work here much easier so that we won't have to do all of this complicated simplifying inside a limit. But in order to establish those formulas, we'll need to use these kinds of tools and this definition of a derivative that we just looked at. So it's good to get some practice. This is a good chance to see how these algebra tools work in the context of finding derivatives of functions. Let's take a look at a few examples involving finding a derivative of a function. The first one we'll look at will involve finding the derivative of the x cubed function. So our goal here is to find f prime of x, given that f of x is equal to x cubed. And we're going to need to use the formula for expanding a third power of a binomial. So here's the general formula. If we have a binomial a plus b and we're cubing it, that's equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. There are a few different ways to derive this formula. If you're interested, you can do it by using repeated applications of polynomial multiplication techniques. Multiply a plus b by itself, and then multiply the result by a plus b again. You can also use something called Pascal's triangle, which you might have seen at some point in your study of algebra. If you're interested, you can find lots of resources to come up with this formula, but there it is for us, and we're going to make use of this. We're trying to find f prime of x, which can be defined as the limit you see here. The limit as h approaches 0 of f of x plus h, that's x plus h cubed, minus f of x, which is x cubed here, all over h. And if we apply our binomial expansion formula to x plus h cubed, we get what you see here up in the numerator. Notice in the numerator, we have x cubed minus x cubed with some other terms in between. And so those combine to 0. So this is what we're left with after we combine those like terms. And now, as we've seen several times when looking at these kinds of limits, we have a fraction in which every term in the numerator and denominator has a factor of h. So we can cancel that common factor of h, and we're left with this limit here. The limit as h approaches 0 of 3x squared plus 3xh plus h squared. This is a limit we can find by substitution. We'll plug 0 in for h. And if we simplify a bit, we end up with plain old 3x squared, and we're done. So this tells us that 3x squared is the derivative function for x cubed. And if we pick a particular value for x and evaluate 3x squared at that value of x, that will give us the instantaneous rate of change of x cubed at that value of x. Or if you prefer, the slope of the tangent line of the graph of y equals x cubed at the point where x has that value. Let's take a look at a second example. This time we'll find the derivative of the square root function. So in this case, we'll use Leibniz's notation this time, although it won't change very much. We're going to find dy dx, the derivative of y with respect to x, if y is equal to the square root of x. Again, we'll use our limit definition of a derivative. Dy dx will be the limit as h approaches 0 of what you see there, the square root of x plus h minus the square root of x over h. This is a little complicated to simplify, but this will work. We are going to multiply the numerator and denominator of the fraction inside the limit by the conjugate of the numerator. That's what you get if you change that minus sign joining the roots to a plus sign. This looks like it's kind of unwieldy, but as we'll see, this makes things work out nicely so that eventually we'll be able to find that limit by substitution. If you do the multiplication here, in the numerator, you'll end up with just x plus h minus x. That is the square root of x plus h squared minus the square root of x squared. And of course, squaring the square root cancels the root. In the denominator, we just have h times what you see on the right, the square root of x plus h plus x. Of course, in that numerator, we can cancel the common terms or the like terms. X minus x is 0. And now we can cancel the factor of h that you see in the numerator and kind of in the front of the denominator there. And we're left with this right here, the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And we can find this limit now by substitution. If we let h be 0, we won't end up with 0 in a denominator or anything else that would make this expression undefined. So let's do that. We'll plug 0 in for h. And if we simplify, we end up with 1 over 2 times the square root of x. That is the derivative function for the square root of x. And we were able to find it, again, by using this limit definition of a derivative and this little algebraic trick of multiplying by a conjugate. Our third example will be slightly different. We're going to find the derivative of the 2 over t function, but this time we'll find the derivative at a particular point rather than finding a general formula for the derivative. So we can express our problem here like this. We want to find dy dt at the point where t equals 3 if y is equal to 2 over t. Notice here that the independent variable of our function is t rather than x. That's why we're finding dy dt, and then we're given a particular value of t. There are two ways we could do this. We'll look at one of them. The way we'll use is to find a general expression for dy dt in terms of t, and then we'll evaluate that expression where t equals 3. You could also do this by plugging 3 in for t or a or whatever you want to call it in the definition of the derivative to get started. You'll get the same result either way. So let's start by finding a general expression for dy dt. It will be this limit. The limit is h approaches 0 of 2 over t plus h minus 2 over t all over h. This is our general definition of a derivative applied to 2 over t. And to simplify this, we'll start by getting a common denominator inside that numerator. So our common denominator will be t times t plus h. And if we adjust our numerators accordingly and then combine the fraction, we get this right here. We're skipping over some of the algebra steps here. I'm confident that you can do those yourself. And if we simplify a little further by combining some like terms and getting rid of the complex fraction that you see there, we get this right here. The limit as h approaches 0 of negative 2h over h times t plus h. By the way, that looks like h of t there, like it's a function expression, but it's not. Here I'm writing that to mean h times t plus h in the denominator. That's the use of parentheses to denote multiplication. We can cancel a common factor of h now, and we're left with this limit here. And we can now find this limit by substitution. We'll let h be 0. And if we simplify, we get negative 2 over t squared. So there is our derivative function for 2 over t. We're not done though, because our goal is to find the derivative at t equals 3. So at this point, we'll take that derivative function, negative 2 over t squared, we'll let t be equal to 3 inside of it, and we'll evaluate what we get. So dy dt at t equals 3 will be negative 2 over 3 squared, or negative 2/9. There is the value of the derivative of 2 over t at t equals 3.